Hello. So today we will look into regularization with normal equations. In the previous video, where we dealt with regularization in terms of the gradient descent algorithm, we had seen that in a certain situation where we have 5 training points, we could get a straight line like this as a solution, which looks very much like a natural fitting line. Or we could tweak our parameters, add more dimensions and get a straight line, which is quite complex, but it is fitting the data better with the loss being lesser than the previous one. But this is what we say is a overfit line. And we wish that our model should generalize beyond the training set. The aim is not only to fit the training set well, but also to generalize well. So we do not want an overfitting line. So we would penalize the size of our weights, put a penalty. So in terms of normal equations, we have seen previously, I'll give you the link in the description box, that using the normal equations or with the help of normal equations, the optimum weights for the solution by linear regression is found in this manner. With regularization, we make these changes. So we have added this component. So it is nothing but lambda multiplied by a matrix whose dimension is d plus 1 cross d plus 1, where d is the dimension of the, the data. Okay, so this matrix is d plus 1 cross d plus 1. And then we take, like here we were taking only the inverse of this component xtx. Now we are having xtx plus lambda into this inverse of this multiplied by xty. For 2 dimensions, the matrix would be this 0 at the first primary, the position of the primary diagonal, and 1s on the rest of them. So now solution. So we have this x and y. Again, we have solved this example previously. So we have this xy, and we know that we write x in this manner because this is x0. This column belongs to the 0th dimension, or the dimension corresponding to the bias weight W0. This is our x, and we have this y, and this is the solution we want to find with regularization. So we write down the components. So this is our xt into x, which we have solved earlier. This is lambda into the matrix. This is the dimension of data is only 1, this one. So we matrix is 2 cross 2, 0 here and 1 in the second position of the primary diagonal. Inverse of this matrix and then the rest of the components of x transpose y. When we solve for W0, W1, we get this value for no regularization. For lambda equal to 0.5, we get a certain set of solutions, and for lambda equal to 1, we get another. Visualizing these solutions, we get these 3 lines. Even though visually it is difficult to differentiate, however, these are different lines corresponding to the W0 and W1. Now, which one? See, this is regularization we have applied using different values of the lambda parameter. Okay, when you are actually applying it to your applications, how do you decide what is the best lambda? That is done based on the validation set. In another example, we will see in the future video, we'll take the training set and the validation set. So then we will be able to decide which lambda we would proceed with. And that is the usual method we would be taking when we train our models. We decide our parameters based on the validation set, and then we train the model in the final form. So I hope the concept of regularization is now clear to you, having gone through the previous video and this one. And thanks a lot. Thank you for watching.